Did you see that? I've attached a microphone to my blackboard. Every time I made contact with the chalk, you saw the sound wave being displayed on the oscilloscope. Fundamentally, this is how seismology works. Seismology is the detection of small earth tremors, sound waves passing through the Earth's surface, basically using very sensitive microphones and trying to detect the sound of parts of the Earth moving perhaps thousands of miles away. So here is an interesting demonstration. The Earth, as we see it from space around the ball, is not entirely solid. In fact, inside it has structure. As you go down deeper and deeper, the density gets higher and higher, becomes more compact, but the temperature rises also, to the point where a small part of the inner workings of the Earth is liquid, and within that a solid object still. Now we can create a very crude model of the inside of the Earth using a plate and a petri dish. Now what I'm going to do, I'm going to pour a nice high density substance, in this case some glycerol, into the petri dish, and it goes, and we'll get it to the point where it's just about to overflow. Now the second thing I'm going to do is I'm going to pour some water. And what I'm going to do with this water is I'm going to add a few crystals of fluorescein, just a little tiny bit, just because. In we go. And that will make it nice and luminous to represent. Okay, in this case, nothing inside the Earth is luminous, but it just helps us to see the distinction of the two different areas. I'm going to very slowly pour this in. Now I'll bring you closer so that you can get a better look. I want to get it to the point where the two liquids are almost in contact. Like that. There. So this is a representative of the inside of the Earth. We've got this more viscous fluid deep down. It's a very crude model. But watch what happens when I send waves. The root cause of earthquakes is a build-up of pressure between the Earth's tectonic plates. And these are on the surface of the Earth, in the Earth's crust. Now we know, by studying earthquakes, a little bit about the interior of the Earth. What is inside this thing? If we were to take a slice out of the Earth, we would end up with something that looked a little bit like this. That you can see that the main parts of this include the Earth's crust, which is the part of the Earth that we are standing on. Divides into two types, continental crust and oceanic crust. But this is tens of miles thick. Then we end up with a region that is solid. This is the mantle. It is rock under huge pressure, and it gets warmer as you go down. Then inside that we have this liquid outer core. Why is it liquid? Well, basically the rock has melted, and in fact deep down inside the Earth there tends to be less rock and more iron, and so this is basically molten iron. Occasionally the pressure can get so great on the crust that the rocks start to melt, and as a result what sprays out is lava or magma, but generally speaking, this is not a conduit down to the liquid outer core. This is just some pressure localized on the surface. Now, within the liquid outer core is a solid inner core. The fast rotation of this iron object, faster than the rest of the planet, is what creates Earth's magnetic field. It's like a dynamo continually spinning and generating magnetic field that erupts out of the poles of the planet. Now, when there is a build-up of pressure in the Earth's surface, what happens is an earthquake will occur. A sudden movement can cause the shaking of the ground. Now, the most obvious type of shaking is the shaking that takes place forward and backwards. If you see footage of an earthquake, what you see is the ground shunting backwards and forwards. Now, these are P waves. P waves are longitudinal waves, so kind of like sound waves going through the ground with compressions and rarefactions, causing a movement of buildings and structures. This is normally the reason why things fall down. If the bottom of the building suddenly moves, the centre of gravity lies outside the footprint and the building can fall over. So P waves are really interesting because P waves can travel as compressions through any medium, including fluids. Being just like normal sound waves means that they can travel through, well, there's no gas down there, but they can travel through liquids and they can travel through solids. So if this point here is the source of an earthquake, then what happens is the P waves radiate like this through the solid sections. But then what happens, some of them actually get into the core and appear on the opposite side of the world. And so some P waves actually travel all the way through the planet by travelling through the core. By measuring the appearance of the P waves elsewhere, we can actually measure what's inside the Earth. A different type of wave, one that you see not so much, is the S wave. S wave. It is a transverse wave. It is an up and down movement of the Earth. These are not as common and not nearly as strong. The thing with the S waves is they're not a compression of a medium. They're a sideways oscillation of a medium. And you can only have that if the medium is connected together. In a fluid, it's not. It can move. And so it doesn't get into the liquid outer core of the Earth. In fact, what happens from our earthquake with the S waves is we detect them going through the Earth like this, but we don't detect any on the other side of the world. By setting up seismographs around the world, what we're able to do is listen to those sound waves travelling through the Earth and building up a picture of what is inside.